We've been talking a lot about the application of artificial intelligence for science, and one of the areas where we personally are very interested in is actually material science. Material science, in our opinion, and when I say our, I mean from the perspective of Orange Capital Partners, which is the hedge fund that is actually behind this podcast series. Um, uh, we we believe that material science has a large role to play in some of the most important industries of the future, whether that is the electrification of our transportation industry through better solar panels, better nuclear reactor designs, better electric car batteries, better charging infrastructure. So you see, wherever we go on every vector that we're trying to influence the future of these types of industries, material science actually plays a key role because in the end, it comes down to the material. It comes down to what's called reverse design in the industry, which is we want to have certain properties. Actually, the canonical example of that would be the Starship heat shield, that according to Elon Musk is the biggest problem now for Starship. It is you want to bring that thing into orbit, which of course is a propulsion problem. But how do you bring it back from the I mean, how do you bring it back into the atmosphere, and how can you make it reusable? You need a heat shield. You need to protect this massive, 10-story building that flies up and down uh, from into the atmosphere and back, and so forth. How do you make sure that that thing doesn't, just blow up because of the heat differences that it has to go through? We have a lot of problems like that, in particularly in sort of more newer innovative industries. And the key question is, how can AI, if at all, help in this particular space? And of course, the answer is AI can help a lot, because AI is a tool that helps science iterate much faster over an action space, or actually two things. It helps reduce the search space and improve the action space. So I want to discuss this. I have a link by a PhD thesis defense from a few years ago from the University of Utah. Links in the show notes. Kudos to Taylor Sparks, who is running this series. He's a professor there. Very interesting stuff. I am not a material scientist myself, so I'm not going to go into the details and the nitty-gritty of actual science. I want to keep this at the AI level. And what I really want to ask here is, can we bitter pill, excuse me, can we bitter lesson? Can we bitter lesson this space? Because it seems to me that science is a little bit caught in a representation problem. I'm going to explain what that means in a second, but just here in the prelude, think about it. Like, for example, in chemistry, we're using the periodic table, which is, of course, a fantastic way to represent chemistry, but it's a 19th century technology that might or might not be useful for today's representation of chemistry when it comes to machine learning. What helped us in the 19th century, start define things, turn chemistry or turn alchemy into chemistry. What helped us do that, which was, of course, a big, amazing um, endeavor, it might actually not be the right way to represent. I think the question of representation in AI is a fundamental question that often gets overlooked. And that's because people just like naturally to work on algorithms, on techniques, architectures, but the actual representation, or in plain English, the kinds of data you need to feed these algorithms in order to actually produce useful results might be different than what you think. And I'm going to use examples, particularly ImageNet, in my opinion, is a very good example of that. But again, the question that I want to ask here is simply, as a scientific endeavor, material science, and I'm going to focus on material science. You can explore further aspects of science, such as physics and chemistry, but let's stick with material science because this video that I put in the show notes inspired this episode. So let's stick with material science. I'm just saying, like, what is the goal and how can we get there? And I think the goal is to get better predictability of what kind of materials we could use in order to solve problems. Let's take the heat shield of Starship as a canonical example. And can we narrow down the search space and increase the usefulness of the action space? In other words, can we narrow down where we look for and then also bring better candidates to the surface that we can then test in the real world? Because, sim to real is always going to be a problem. Whatever we can do in simulation, whatever AI can come up with, has to be tested in the real world. So there's always going to be a sort of a gap that needs to be filled, and that probably, for a long time at least, can only be filled with actually real world testing. The reason I'm saying that is that even in chip design, which is, according to Jensen Huang, fully automated at this point, it's fully virtual, and only the tape out is actually, well, the tape out means whenever you're done with the design of a chip in virtual space, you then tape it out into the real world. Even then, you might have to actually reconsider stuff, redo stuff. So there's always a sim to real sort of translation issue. That's not going to go away. But of course, you can reduce that massively. And in the case of Starship, imagine if you could come up with a design that has a much, much higher likelihood of being the right design. So then when you actually test the thing and the thing blows up, it just blows up fewer times until you get to a place where you can actually use the thing and become a commercial enterprise. So that's the goal. This is not even on podcast. It's it's July 28, 2025. This is Krim Delco. For the day, we're up 3%. The market's up 6 basis points. For the year, we're down 10.4. The market's up 8.6. We're underperforming by 19%. So we have this really interesting PhD defense, which is materials informatics. So it's the combination of AI or informatics. Actually, let's call it informatics because that's how they call it, and material science. So the idea is, can we use information and in useful ways to do better material science? That's the idea. And there's 3 sections in this particular presentation. One is novel materials discovery. One is Bayesian optimization, and then self-driving labs. What the author means here is that in one case, we can somehow, maybe through some sort of Euclidean proximity or some search method along those lines, find material structures that could be more useful for certain problems to be solved. And in order to get there, we first have to discover them. So we could maybe, I guess the way I understand this is that we have certain known materials, and then if we maybe could find similar, molecular structures that have some sort of proximity, Euclidean proximity, which of course already brings us to the question, okay, what does that mean? How do we represent that? But I'm going to get there in a second. My point here is, again, we could discover novel materials by simply comparing stuff and looking at patterns of molecular structures. Bayesian optimization, that goes into the direction of reducing search space. What that means is that we want to use past information to better predict where to look in the next step. So if we have something like a reinforcement learning algorithm or something similar to that, an algorithm that actually adapts to new environments, and an algorithm that is adaptive as far as the environment is concerned, we might find a more useful way to represent the search space and reduce the potential candidates for search space. That's Bayesian optimization. Self-driving labs is the sort of logical conclusion of that. If we had an adaptive system that can better find, reduce the search space, and in plain English, find better things to do as a next step that have a better chance of success, well, maybe we can automate that, and then we have the concept of robotics. In the case of the presentation, we're talking about one-legged, one-armed robots, things like that. Of course, we could expand that into humanoid robot space. I think that's a very interesting topic on its own. A self-driving lab also has one of the biggest, advantages, in my opinion, is that it's not human. And a lot of science is driven by things like vanity and peer pressure and all that stuff. And if we had a fully automated lab, if we had a robot actually doing research, you could also do some much more interesting research, because the robot doesn't care about tenure. The robot doesn't care about being invited to a conference and being considered a superstar and all that stuff. A robot just, could be optimized for finding better solutions. And a lot of these robots would fail, but some of them wouldn't, and that's kind of how we progress as a society. So that's in a nutshell what this presentation was about. As I said, I'm not going to go into the nitty-gritty. This is not a material science podcast by any means. The purpose of this podcast is to give people a sense for what it feels like to run a hedge fund. So why do we even talk about material science? Why do we talk about PhD defenses here? Well, because we are in the knowledge business. So any kind of knowledge, any kind of idea, any kind of intellectual endeavor that could potentially be useful for our end goal, which is to generate wealth by investing in fundamentally new concepts, engineering practices, anything like that is useful. We talk about novels here, we talk about interviews of CEOs, we interview CEOs ourselves. I mean, we do all kinds of knowledge work, and this is just part of it. So what we think is really interesting is the application of artificial intelligence towards industry, towards, in this case, material science. Jensen Huang just yesterday in an interview on the All In podcast said that he thinks that the factory of the future, the actual industrial operation of the future, will have two factories. It will be the manufacturing factory and it will be the intelligence factory. And we believe that that is definitely a direction worth pursuing. Let's just say that. It's a direction worth pursuing, and finding better AI representations in order to do material science could be a first step towards that goal. Now, what do we mean with finding better material science representations? What does that even mean? The question is really, if you go back, if you dial back the history of AI, and you look at how artificial intelligence has evolved in the last, call it 50 years, I think it started with this idea of some sort of symbolic representation of reality that we try to feed into computers and then use computer logic to make decisions. And that has been the approach of AI until the ImageNet moment in 2012. And the reason that has been the approach is because it's kind of anthropomorphizing reality. It's like we humans do the same thing. We have our frontal cortex, which is sort of the CEO of our nervous system, and we have this illusion of things like logic and rational behavior, when in reality, of course, we're way far away from there. And we know that for sure because we have something called emotions, which is all the other stuff that our nervous system is dealing with that we can't rationalize, actually. So there's a lot more knowledge that we gather on a daily basis than just the sort of logical, rational thinking. It's part of it, and it's useful, and it's helped us a lot in getting, building Golden Gate bridges and computers and things like that. But it's not the only thing. And I think representation of nature in general requires a lot more than just some logical, formal definition of things and things along those lines. And I think the same thing applies to the artificial neural nets that we're building right now. And ImageNet was a great example because until ImageNet came along, the people who were working on neural nets and general representations of reality and things like that Dick Sutton called the bitter lesson, which is large general models with large diverse data. People were working on those types of approaches towards intelligence. They were basically the backwater of AI research until the dam broke, which is with ImageNet and AlexNet and so on and so forth. For people who are not familiar, just go Google this stuff. I'm not going to spend time now on this. But the point was that we found a way to represent, in this case, image classification. We found a way to represent that in a general way without actually telling the models what a cat is, without telling the models what a whisker is, what the difference between a cat and a dog could be, or any of that stuff. We just fed the model a lot of images of cats and dogs, and the model was able to classify those things. This was the big breakthrough because it showed the world that a general representation of reality, a very general representation of reality with a general data structure and lots of compute can actually lead to better results. Fast forward to the transformer architecture in the 1718 type time range, 2017-18. What happened there is that researchers were on this path towards finding a representation of reality in what's called latent space, so representing relationships between words and tokens, which is not necessarily words, but let's call it a unit of compute in intelligence space. So relationships between those tokens at scale, so meaning lots and lots of relationships, lots and lots of different relationships at scale, can actually yield a type of intelligence that transcends all kinds of tasks. So in other words, if we train a language models based on a transformer architecture, we can do translation, poetry writing, marketing material writing, question answer sessions, all kinds of things. We can do them much better than agents which are trained specifically for those tasks. And the reason that that is the case is because, and this is still kind of an open question in research, but I think we're kind of getting there. It is what we call the Platonic representation of intelligence. It's the Anna Karenina model of intelligence, which means that all happy models are alike. In other words, there is some representation of intelligence, something in latent space that captures intelligence, which is not necessarily visible to us straightforwardly. So we don't quite see it, but we know it's there, and if we can find a way to represent it, we can actually take advantage of it, and transformer models are a first approximation of that particular feature. So the question now in this episode is, okay, can we do this also for science? In particular, material science. Is the representation of materials the way we know it now, which is the periodic table, atomic numbers, electron stuff, all the physics stuff that we know, is that the right path? And if so, how can we represent all this data in a way to mimic what happened in the large language model space and take advantage of a large general model with large diverse data, and then hopefully get to the point where we can actually do very similar things like we can do now with large language models. That's the idea. I don't have a solution here, but my suspicion is, or my feeling is, that we're kind of caught a little bit in a representation, cul-de-sac here, which is we're using representations from the 19th century, such as the periodic table, for example. We're using representations from quantum physics, quantum chemistry, valence electrons, dipole structures, and these things might or might not be useful. That's the big question. And right now, I think the results speak for themselves, which is we really don't have good results. Elon Musk said that even in his companies, AI is not being used for material science. Whether it's Tesla or SpaceX, I don't think they're using material science in any meaningful form to advance their technologies. And that's a problem. That's a problem because I think we have the tools now, we have the intellectual capacity to do better. And I think in order to do better, and this is now a suggestion, a conjecture, I think we need to maybe lean back a little bit, take the bitter lesson more seriously, and think about a better representation for scientific knowledge that then can be fed into maybe transformer-like models and used for, in very similar ways like large language models are being used now, for a much, much more effective intelligence. This is the idea. I think I'm going to have to talk more about this in the future, because this is definitely uncharted territory for us here at Orange Capital Partners, investment-wise, knowledge-wise, but it's something we're very interested in. Personally, my son is just starting a physics undergrad curriculum at Berkeley, so he's an ongoing scientist that, in my opinion, will have to deal with these questions much more intensely. In other words, if he doesn't actually jump on this bandwagon and think very hard about the representation of physics that can be useful for AI, then I think he won't be doing the job that he's supposed to be doing. So this is really serious. It's a serious question. It's a series of questions that should be asked at every scientific conference going forward, particularly those that include AI into their curriculum, that we should be thinking about how to represent data in the most general way possible, to then use the most general possible models with a large diverse data set and lots of compute to get answers like, for example, reverse material design, which I think is the holy grail of material design. So we want to have a property, and we then go back from the property towards the actual material. So things along those lines. Maybe approaches like AlphaFold in the protein space can be used for material science. I think DeepMind is working on issues like that. So there are approaches, but I think the problem, again, it's not on the algorithmic side of things. It's fundamentally still at a representation level. Thank you.